So today we're going to be proving this theorem. And this theorem says that if we have a function and this function has a limit at a point C, then that limit is unique. So it's saying we can't have the limit as x approaches 2 of f of x equals 3 and the limit as x approaches 2 of f of x equals 4. That can't happen. Alright, so how are we going to approach this? So our main tool that we're going to be using is we're going to argue by contradiction. We're going to assume that this function has two limits, L and M, and then show that those limits are equal to each other. So we're going to argue by contradiction. So we're going to assume, this isn't our proof, this is just our ideas. So we're going to assume that the limit as x approaches C of f of x equals L, and the limit as x approaches C of f of x is equal to M. And then, once we do that, we're going to follow the definitions and we're going to show that L equals M. And the way we're going to do that is we're going to use a handy little, result from about real numbers, that if we can make the distance between L and M arbitrarily small, then L must be equal to M. Okay? So we're going to assume that this function has two limits and show that those limits are equal to each other by showing that we can make the distance between those two limits arbitrarily small. So let's start off our proof. Okay, so our first step is we're going to let epsilon be greater than 0. Actually, we need to first argue by contradiction first. So we're going to assume or suppose, for the sake of contradiction, let epsilon be greater than 0 will be our second step. So we're going to suppose, for the sake of contradiction, that the limit as x approaches C of f of x is equal to L, and that the limit as x approaches C of f of x is equal to M. And we're going to assume that L is not equal to N, where L is not equal to M. And if we can show that L does equal M, then we will have arrived at a contradiction, and thus we can assume that a limit, if a function has a limit, then it must be unique. Okay, now we're going to let epsilon be greater than 0. Getting kind of messy here, maybe a little bit. Let epsilon be greater than 0. Okay, so now we're just going to kind of follow what we know. So we know that if the limit as x approaches C of f of x equals L, then there exists a delta, but here we're going to call it delta 1 because we're also going to have a delta when we follow the definition of this limit. So we're going to call it a delta 1 greater than 0, such that if the absolute value, so if 0 is less than the absolute value, such that for every x in A, if 0 is less than the absolute value of x minus C is less than delta 1, then the absolute value of f of x minus L is less than epsilon. And that right there, that's just the definition of the limit. We just said, okay, so we're supposing that the limit as x approaches C of f of x equals L, then this just follows directly from the definition. Okay, so similarly, we can do the exact same thing with this limit. But there's one more thing we want to change, is we don't want this to be epsilon. We want this to be less than epsilon over 2, and this will be apparent later. Right, we're going to use the triangle inequality, and we're going to want to end at epsilon. So we're going to want an epsilon over 2 right there. Okay, so similarly, so since the limit as x approaches c of f of x equals m, and then just from the directly from the definition, there exists a delta 2 greater than 0, such that for all x and a, if the absolute value of 0 is less than the absolute value of x minus c is less than delta 2, then the absolute value of f of x minus m will be less than epsilon over 2. Okay, so we just suppose that these limits existed, and then we just applied the definition of the limit. Okay, so now we're going to let delta be the minimum of delta 1 and delta 2. So let delta be the minimum delta 1 and delta 2. Then if the absolute value of 0 is less than the absolute value of x minus c is less than delta, what do we got? Okay, so remember, we're going to use this tool that the absolute value of L minus M is less than epsilon. Okay, so we're going to have the absolute value of L minus M, and we want to show that that is less than epsilon. How are we going to do that? So we're going to use a common trick that is common in analysis, is that we're going to add and subtract f of x. That way we can use these inequalities right here. The f of x minus L is less than epsilon over 2, and the f of x minus m is less than epsilon over 2. So we're going to add and subtract f of x. So this is the same thing as L minus f of x plus f of x minus m. Okay, and now we can apply the triangle inequality. So this is going to be less than or equal to the absolute value of f of x minus L plus the absolute value of f of x minus m. Okay, and since x is inside this little delta neighborhood here, then both of these things are true, that f of x minus L is less than epsilon over 2. And similarly, f of x minus m is less than epsilon over 2. So f of x minus L, that's less than epsilon over 2. F of x minus m, that's also less than epsilon over 2. So we get that the absolute value of L minus m is less than epsilon for all epsilon greater than 0. So that means that L must equal m, right? Because the absolute value of L minus m, it can't be 1 because it's less than 1, we just showed. It can't be 10 to the negative googolplex because we showed that the absolute value of L minus m will be less than that. So the only possible answer is that L must equal m. So therefore, L equals m, which is a contradiction because we assumed at the start that L does not equal m. So that is a contradiction. So what can we conclude? Well, we can conclude that if a function has a limit at that point c, then that limit must be unique. So we'll end it right there.